Hi folks, this video and the next are going to cover the methods involved in going from a geologic sample, such as a rock, to an isotopic measurement of that sample. Typically, mass spectrometers work best when measuring the isotopic composition of an elementally pure sample. For example, if we are hoping to measure strontium isotopes in a rock, we want to load just the strontium atoms from that rock into our mass spectrometer. If we want to measure uranium, we only load uranium atoms, and so on. If lots of other atoms are present, they can interfere in various ways and ultimately result in a lower quality isotopic measurement. So, to get pure separates of atoms like strontium, uranium, thorium, neodymium, etc., out of geologic material, we first convert our geologic sample into a solution by dissolving or digesting that sample. Then, we extract the element or elements of interest out of that solution so we can finally load those into a mass spectrometer for isotopic analysis. In this first video, I will focus on the wet chemistry methods we use to dissolve geologic samples and purify the elements of interest. The following video will entail a tour of a mass spectrometer and loading our purified samples into a thermal ionization mass spectrometer, or TIMS. Throughout this video, we'll also follow the journey of B176 as we use these same methods to measure its uranium, thorium, and strontium isotopes. Let's begin with sample digestion. In this step, we take geologic samples, which are often solid, and ensure that they are fully dissolved as salts in an aqueous solution. So, we'll start with our geologic sample itself. At this point, we have isolated an aliquot or aliquots of our sample. Aliquots are pieces of that sample that we might individually measure in some meaningful way, such as rock fragments or individual mineral crystals. Each of these pieces that we measure is called a fraction, so let's place one of these fractions into a beaker. Then, into the same beaker, we will introduce digesting solutions, in which our fraction is soluble, or readily dissolved and converted from solid sample to ionic salts within a solution. This is typically accomplished using strong mineral acids like hydrochloric acid, hydrofluoric acid, and nitric acid. But different geologic materials may require different methods for complete digestion. In some cases, we will also add an isotopic tracer, a solution of a special isotope of an element of interest that we can use to measure the amounts of the different isotopes of that element in our sample by using the techniques of isotope dilution. Don't worry about isotope dilution too much now, as we'll come back to it later in this course, but this is typically the step when we add our tracer. Here's our crushed sample from before. We'll start by storing them in pre-massed vials and measuring the mass of these with a sensitive balance. Alternatively, we can mass our fractions directly on tiered weighing paper. From here on out, we will be doing the rest of our chemistry in clean lab spaces. I will be working either within a laminar flow bench, which blows a sheet of filtered air to keep the workspace free of dust and debris, or I will be working within a laminar airflow fume hood, which pairs the cleanliness of a laminar flow bench with the ventilation of a fume hood to protect us from hazardous acid fumes. After noting the mass of our sample, we then want to clean off our samples before digestion. This means removing any dust or soluble material that is not contained within the carbonate mineral matrix of our sample. Cleaning methods vary broadly depending on the type of sample, but carbonate minerals are often cleaned with an organic solvent like isopropanol, acetone, or methanol. Here, I am pipetting methanol into the vials. Then, these vials containing the samples and the methanol are agitated at room temperature in an ultrasonic bath, which uses high-frequency sound waves to produce tiny bubbles that collapse with great force, effectively scrubbing the surface of our submerged material. After this, the methanol is pipetted out, and I rinse the remaining fractions several times with ultra-pure water to remove the methanol, dust, and anything else collected in this cleaning solution. I then transfer the cleaned and rinsed fraction into a Teflon beaker. We use Teflon, or the generic term fluoropolymer, beakers for two reasons. First, because fluoropolymers like Teflon are resilient to many strong acids and other strong reagents. The other reason is that these compounds tend to have very low contamination of trace metals and are easily cleaned of trace metal contamination. All of our Teflon beakers are pre-cleaned in strong acids prior to touching any of the samples. Here they are on a heated hot plate with cleaning acid inside of the sealed beakers. After cleaning and rinsing the sample, now I add nitric acid to dissolve the carbonate, as well as a mixed uranium and thorium isotopic tracer. Then we cover our beaker and place it on a hot plate so that heat can help speed up the digestion process. With this beaker capped and heated, the acid will evaporate, condense on the cap, and rain back down on the sample, a process we call fluxing. Once dissolved, the water and nitrate can be evaporated away, leaving behind the salt residue of the dissolved sample. This salt is easily redissolved in acidic solutions. Once our sample is fully dissolved, we are ready for elemental separation. To purify out our elements of interest, we typically use some form of ion exchange resin, an organic compound that bonds with different elements under different chemical conditions. The resin is housed in a column, so we often call these methods column chemistry. First, let's meet the resin, an organic compound coated over small plastic beads. These fine beads are readily suspended in water and loaded into the column. The column is a simple tube with a filter at the base that allows fluid to pass through but prevents the resin from exiting the column. So, our column starts with a reservoir that we can load different solutions into called eluents or eluants. These solutions then pass from the reservoir into the column neck, which is filled with resin. The eluent flows through the resin and out past that filter called the frit and exits the column as the eluate or elutant, while the resin remains within the column neck. The resin bed is where all of the excitement happens. This diagram zooms in on the resin bed with the eluent entering above and exiting as elutant below. The importance of ion exchange resin comes from their affinities for different elements or molecules under different eluent conditions. So, under certain chemical conditions controlled by the eluent, the stationary resin forms ionic bonds and holds onto certain ions, such as strontium, uranium, thorium, neodymium, and so on. We can then break these bonds by changing the eluent. So we load our sample, including the analyte, the atoms that we want to purify. The dissolved load is introduced onto the resin in a loading acid. Dissolved in the loading acid, the analyte ions bond with the resin and stick to it, while the matrix ions, all the elements that we don't care about, pass through and leave the resin with the eluate. A different acid is introduced into the resin that disrupts the bonds between the resin and the analyte, releasing it so it can be collected with the elutant. This solution contains purified analyte and can then be prepared for introduction to a mass spectrometer. This time-lapse video speeds up the dripping by a factor of 10. The column is shaped so that the solutions pass through slowly, draining out the bottom of the column one drip at a time. This gradual process is key so that the eluent slowly percolates through the resin and gives plenty of time for the analyte atoms to react with the resin, whether forming or breaking bonds. So to see this in action, let's look at how we purify uranium and thorium separates from dissolved fractions using Ag resin. First, we start with our beakers containing the dissolved fractions. We need to first get them into loading acid from their digestion acid. By removing the beaker caps, we evaporate away the water and nitric acid, leaving behind the salt residue. We then rehydrate the solution in our loading acid, 7 molar nitric acid, and they're ready for columns. While the loading acid is pipetted onto the column, only uranium and thorium stick to the resin in 7 molar nitric acid, while matrix ions, such as iron, sodium, and calcium, are lost with the elutant. Strontium atoms are also in the solution, so I will collect the solution in a beaker and save it for further purification on a different column. Then we switch to 6 molar hydrochloric acid, which releases thorium from the column. We collect this elutant because it contains our pure thorium separate. Finally, by passing pure water over the column, uranium is released, and we collect that elutant with our purified uranium separate. Our matrix solutions with strontium are then rehydrated for strontium purification on a different column with a different resin that is optimized for strontium separations. Finally, we completely evaporate all of our purified separates in a drop of dilute phosphoric acid to prepare them for isotopic measurements by TIMS. You can see how much smaller these dried drops of pure uranium and thorium are, containing very, very little material compared to the original rock. In fact, most of what you can see in these specs is just the dried phosphoric acid. So, these samples are now ready to load onto the TIMS, which I'll show you in the next video. See you then!